Lesson 11.5 is all about infinite geometric series. Now again, a geometric series is where you would add up all of your terms from a geometric sequence. So if we had, say, 8, then 4, then 2, then 1, so we're just reducing by a half each time, so we get 1/2, 1/4, 1/8, and continue on, cutting it up in a half time each time we change it, and then we added all those up. That would be a geometric sequence that we're adding together, but let's say we wanted to add them up forever. So we keep going on, adding up all of them until forever over here. We just keep on going. If we were to add all of those up, that would be what's known as an infinite geometric series. Now, not all geometric series will have an infinite sum. Sometimes they'll get just too big, and they'll continue on getting bigger, and we'll never know exactly what they equal. So which ones do? How do we know if they have a sum or not? Well, we'd say 1, or negative 1 is less than or equal to that r value is less than or equal to 1. So the r, our common difference, has to be in between negative 1 and 1. And it can be exactly equal to them, but it just has to be within that range. Another way to say this is the absolute value of r has to be less than 1. So these are our two stipulations to check and see if they are. So like this one, to go from 4 to 8, 2 to 4, that's 1/2 is our common ratio each time. Again, we're just, like I said, cutting it up by 1/2. So in this case, there would be an infinite geometric series. There would be the sum because it's in between. We'd say negative 1 is less than or equal to 1/2. That is less than or equal to 1. That is true. So we could find the sum of this one. So let's see how it works for these ones. We need to know, first off, what is that r, the common ratio, to know if we actually can do it or not. So we'd say, how do we go from negative 108 to 36? Negative 108 divided by 36 equals negative 3. Again, just a double check to be sure, 36 to negative 12. 36 over negative 12, again, is also negative 3. So our common ratio is negative 3. Negative 3 does not hit our stipulations. It's outside of that bounds. It's greater, or should I say less than negative 1 outside of our bounds. So this one does not have an infinite sum. So let's check this other one though. To go from negative 3 over 2 to 3. So we'd say negative 3 over 2 divided by 3 equals 1/2. Oops, I mean negative 1/2. Same thing, if we had negative 3/8 over 3/4, negative 3/8 over 3/4, just to double check, that should be a negative there. Again, that's also negative 1/2. So that is our common ratio here, not common difference, common ratio, and that is within our stipulation. That is, negative 1/2 is in between negative 1 and 1, so this one does have an infinite sum. So how do we know how to find the infinite sum? Well, our formula then is our sum of all the infinite numbers, so the sum of an infinite amount of terms. So we'd say either s sub infinity, or you can just say s equals a sub 1 over 1 minus r. So it's just essentially the first part of our original geometric series. We just don't have the minus a sub 1 times r to the n. It's a lot simpler just to find the infinite series. So all we have to do then is plug in our values. So we know our a sub 1 is 3, so we'd say infinite sum is 3 over 1 minus r, and r is negative 1/2. So 1 minus 1/2 is going to be 3 over 3/2. So we'd say 3 over 1 times 2 over 3. And the 3's cancel out, so it's going to become 2 in the end. So this will sum to 2 in the end. If you add up these numbers continuously forever, the sum will come out to 2. So if we are given it in sigma notation, again, we would still be using the same S sub infinity equals A sub 1 over 1 minus R. But we don't necessarily know what A sub 1 or R are in these cases. But if we are given any sigma notation value, and it goes from k equals 1 through infinity, and it has an equation with it a times b to the n minus 1. If it's given in this form, we would say that our a sub 1 is this value a right here, and that our r is this value b. Now all we have to do is plug those back into our equation. So we'd say, in this case, the infinite sum is, here's our a, here's our b. So we would say a, or 5 on top, over 1 minus r, which is not negative, but just 1/2. Technically, before we do this, we always want to check and make sure that this r value is it in between -1 and 1, and yes it is. So there is going to be a sum. Now that we know that there is a sum, all we have to do is just solve it out. So we'd say 5 over 1 minus 1/2 is 1/2. So we put it as 5 over 1 times 2 over 1, because we're multiplying by the reciprocal, which means that our sum is 10. So again, we would say 10 is the infinite sum, or you could say just 10 is the sum. You'll see it written both ways. Both are correct. So now that we know how to deal with an infinite series in sigma notation, here's a kind of a neat trick you can use when we're given a number as a repeating decimal like this, and we want to know how to change it into a fraction, or how does a calculator change it into a fraction. Here's a nice cool little method that will help us find how to do that. The first step to do is just write down your decimal and set it equal to d. So actually, I'm going to put d on our left side, say d equals 0.252525, continuing on. Our second step then is to multiply by, normally we don't necessarily know how much we need to multiply by, but we always know that it's however much we need to find that repetition. So in this case, it's 25, 25, 25, so to make it repeat, we need the 25 out front. So in this case, and in most cases, we'll multiply by 100. So that would look like this then. We'd have, 100d equals 25, because we multiplied this side by 100, 0.252525. Now again, let's say our decimal value d was, d equals 0.33333. You don't need to multiply it by 100. You could just multiply by 10, get 10d equals 3.33333. So as long as you have enough so that you're hitting the repetitions, that's all you need, that much of 10. In this case, it's 100, and normally it will be 100. The next step then is we're going to subtract our two equations. So we would say 100d equals 25.2525 ... and d equals 0.252525 ... and we subtract them. There's a little more room to work here. 100d minus d is 99d equals, this whole piece is the same as this, because they continue on forever. So when we subtract them, we're left with just that 25. I'm going to show you the same thing with this piece here. So if we had 10d equals 3.3333 ... and we had d equals 0.3333 ... and we subtracted those values, that would give us 9d equals not point, just 3. Now from here, the last thing to do, step 4, is just solve for d. So in this one, we would say d equals 25 over 99. So that would be our decimal fraction, our 0.25252525. We could say that that's 25/99ths. Or in this case, we would say if we had 9d equals 3, then d equals 3 over 9, or 1/3. So that's why 1/3 comes out to 0.33333333 and continuous. So that's a pretty cool trick there as well. So things for your reference sheet. Anytime we are looking for infinite sum of an infinite geometric series, again, it would be written something like this. S sub infinity is going to be a sub 1 over 1 minus r. Or, again, remember, you might also see it just as the s. S equals a sub 1 over 1 minus r. I prefer it as the s sub infinity, so you know where exactly you're coming from. And remember, it works only if -1 is less than or equal to r, which is less than or equal to 1. So our r value has to be in between -1 and 1. In sigma notation, if we are given an equation that looks like this a value is going to be our a sub 1, this b value is our r. As long as we check and make sure r is still in between -1 and 1, then we just take these two values and plug them in, and that would find our infinite series. And if we want to solve for a fraction, so we're given a decimal, remember the steps are write d equals the decimal value, multiply by 100, or whatever value of 10, so 100, 10, 1,000, 10,000, however much you need to find that repetition. Subtract your two equations, and then solve for d. Otherwise, stay golden.